Alright, so here we have a question about a bug on a rod that rotates. And so we have to do some rotation, torque, acceleration, velocity, that kind of stuff in these questions. So the first one is just simply finding the torque about the axis that's labeled in terms of the things we're given. Right, so we have a rod. The rod is essentially massless. We have a sphere of mass m on one side, a sphere of mass m on the other side, and a bug of mass 3m attached to the sphere. The axis is right in the center. This is length 2L. And so that's enough right there to solve it. So the spheres, we're told, are negligible radius, which means they're essentially point masses. And we're also told the bug is small compared to the length of the rod, so the bug is essentially a point mass. So this can really be redrawn as something kind of like this. And then the total length remains 2L. Right, and that's a little bit easier to see what's going on, because now we can calculate torque quite simply. So if we only had the blue mass, then the rod would rotate that way. That is clockwise, so that's going to be a negative torque. Alright, so we'll start with tau equals, oops, not that one, R cross F. So RF sine theta. So, and actually I should do the other one as well. So then if you only have this 3m mass, it's going to rotate counterclockwise, and so that'll be a positive. So we need the net torque, sum of all the torques, of which we have 2 due to gravity. Right. This orange one is going to point down, and this blue one is also going to point down. So I'll do the positive one first. R, the distance from the force application to the pivot, is L. The force is, oops, I miswrote something up here, so I'm going to fix that. The force, this is not a total of 3 mass, 3m, because I've combined the bug and the block. This is a total of 4m. So the force is 4mg, and sine theta is 1 because theta is 90 degrees. Then the negative torque from the other, also a distance L, and a force of mg. So the net torque is just 3mgl. Right? And it's positive because the thing is going to rotate in the counterclockwise direction, because the bug side is a little bit heavier. Okay. Next step is to figure out the angular acceleration that instant. So to do that, we're going to have to we have a couple different ideas that might work, but the simplest one I think is that we just found torque, so using a expression like that is probably going to be the easiest, because all we need is the moment of inertia. Let's calculate that. We have point masses, so I'm going to use that sort of discrete version of the moment of inertia calculation. And we have essentially 2 of them, right? We have a mass 4m, a distance L from the pivot point, and we have a distance m, a distance L from the pivot point. So our total moment of inertia is 5 ml squared. So now we can solve for alpha. Alright, just plugging in, we can cancel masses, we can cancel length, so we're left with 3g over 5L. Alright, that's the angular acceleration at that instant. It's important to note that the angular acceleration is not going to be constant, because as the rod rotates, the angle between the force of the weight of those two objects and the radius vector is going to change, and so the net torque will change. But that's the torque right at that instant. Alright, and so now we're trying to describe the process when it rotates. We know its acceleration the instant it starts, and we want to know how fast it's moving when it's rotated 90 degrees, so the bug's at the bottom. And so here's where the important fact that the angular acceleration is not constant comes in. Because if you wanted to figure out the speed by doing like something like, if you wanted to do that, this won't work because that's not constant, right? That's your issue. You could do something like this, but that's going to be really hard because you don't know how long it takes, and you don't have the angular acceleration as a function of time. This is going to be a pain. You have to do a lot of algebra or calculus for that, and you don't really want to. So that's really out. None of this will work. I'm going to cross it all out in red. Right? Don't do that. But since we know about speed, we know speed is our question, and we have a before and after picture that's very, very clear. The best option is going to be do something with energy conservation. That'll be much, much, much simpler, because we don't care about the process to get to that point. We just care about how we start and how we end. So I'm going to do energy conservation. The important thing with energy conservation is there are three kind of two objects and two types of energies. So you say, let's write the energy before. Let's just clear all this out of the way so I have a nice clean sheet. Okay, so now we need to do energy conservation. So for our rod in the before picture, we're going to call that the y equals 0. This will be our rod in the after picture, right? That's not 3m, that's 4m. Right. So we're going to call that the position where the bug ends up the 0 gravitational potential energy. So the initial energy is all potential energy, right? It's not moving. And so that's going to be the total mass, because they're the same height, 5m times g. And then this height right here must be L, right? Because here, if that's the center, that's right, the radius of the rod. So 5mgl. The final energy is a little bit more complicated. We have some gravitational potential energy, right, from this mass. So that is mg2l. And we also have rotational kinetic energy. They have the same angular velocity, so we can write that down. I'm probably going to do it in two terms. Actually, I'm going to do it in one, because we figured out the moment of inertia in the previous part, right? This whole object has one rotational velocity. So if I write 1/2 I omega squared, this is what we want to solve for, and it'll be easy because we know the moment of inertia. So we'll put these two things together. We'll say energy is conserved. So 5mgl equals 2mgl plus 1/2. The moment of inertia is 5ml squared omega squared. Right? So we can cancel some things. We cancel a mass and a length from every term. And we can combine these terms pretty quickly. So we'll get 3g equals 5/2 L omega squared. And now we can solve for omega. So we'll get omega squared equals 6g over 5L or omega is the square root of 6g over 5L, right? And that's our angular velocity. Now, and this is a fast step, because we know from the equation sheet L equals I omega, and our object is rotating about like a axis of symmetry, the center of the rod. So I 5mL squared omega square root 6g over 5L. So you can combine that together kind of however you want. I'm not sure if it ever really gets a whole lot simpler. I would combine the 5's and the L's. So m square root 30 g L cubed. Yeah. All right, actually, let's rewrite that a little bit more neatly. So m square root of 30 g L cubed. So how I'd probably combine that. Right, that's moving the 5 into the square root, so we square it, so we get 25 divided by 5, and then 5 times 6. And then also moving the L in, so we get L to the 4th divided by L, and so we get an L cubed, right? And so that's our angular momentum, right? All right, and then finally, we have one last part, and it deals with the force that's required to keep that bug stuck on there and not go flying off. And so since the bug is moving in a circle, the force that the bug must have exerted on it must be a centripetal force, otherwise it would not move in a circle. So we know that means we're going to be involving a centripetal acceleration, and we calculated omega, so I'm going to use m omega squared. Sorry, oops, not mass. I combined it with force already. Omega squared r, right? So we just found omega. So this will tell us the acceleration the bug has to have at that moment to stay on the sphere, basically. So this is 6g over 5L times L, so 6g over 5. Alright, so we have our centripetal acceleration required, and so now we're going to use F equals ma to figure out the force that is required. But we have to remember it's the net force, so the bug, if I drew a free body diagram, and actually do that over here, there's the force, there's the weight of the bug, and so if it's moving towards the center of the circle, then this must be the force of the sphere. Because with anything else, we're not going to accelerate towards the center of the circle. So this is F sphere minus 3mg equals m 6g over 5. That's actually really slow. Right? So F sphere has to equal, looks like, I have to do some common denominator stuff, but the final result is going to be 33 mg all over 5. Right? And the free body diagram here tells us the direction. It must be up towards the center of the circle, right? Otherwise the bug would not move towards the center, or sorry, rotate in a circle and then therefore move to the center.